Hey there, welcome to this explainer. I am so thrilled you're here. Today we're looking at something that is way more than just a boring little square on a chart in your old chemistry textbook. We are talking about hydrogen. Seriously, I want you to think of hydrogen, not just as, a simple gas, but really as the rebellious, incredibly powerful main character of our entire universe. All right, let's just dive right into this.
Everything about hydrogen literally starts with the number 1. 1. It holds atomic number 1. It's the absolute lightest element known to humanity. But hey, don't let its lack of weight fool you. Because of its sheer simplicity, it ranks as the most abundant element in the entire universe. Think about that. Every single star you look up at night, including our own sun, well, it's essentially a massive churning engine powered by this incredible element.
But that cosmic abundance, it translates directly to our home too. Zooming right into our own planet, hydrogen is the third most abundant element on the surface of the globe. And because it's everywhere, and because it holds just so much potential energy, scientists and engineers are increasingly visualizing it as a major future source of energy for humanity. We are literally looking at the fuel of tomorrow, hidden right in plain sight.
Section 1. The Elemental Identity Crisis. Now, despite its abundance, hydrogen actually has a bit of an attitude problem when it comes to fitting into the modern periodic table. It usually just floats at the top by itself because, well, it essentially lives a double life. On one hand, it shares distinct traits with alkali metals, things like sodium and potassium. It's got a 1s1 electronic configuration, meaning it has just a single outer electron, and it routinely shows a +1 oxidation state. But then on the other hand, it mimics a totally different family, the halogens, like fluorine and chlorine. Just like them, hydrogen is diatomic, meaning it naturally pairs up as H2. It's strictly nonmetallic, and get this, it is exactly 1 electron short of achieving a stable noble gas configuration.
So, the crucial point here is that hydrogen just absolutely refuses to be boxed in. It rebelliously differs from both of its potential families. It stubbornly possesses a much higher ionization enthalpy than alkali metals, which basically means it holds onto its single electron much, much tighter than a metal ever would. But it also completely lacks the unshared pairs of electrons that you typically find in halogens. So it's an outcast, for sure, but an incredibly successful one.
Section 2. Harnessing the hydrogen power.
So how does humanity actually tame this rebellious element and utilize its raw power? Well, it requires a massive industrial scale. One of the primary commercial preparation steps is called coal gasification. Imagine taking solid coke, which is this really carbon-rich fuel, and just blasting it with superheated steam. This reaction produces a highly valuable mixture of carbon monoxide and hydrogen, which we call synthesis gas, or syngas for short. And from there, we push it through what's known as the water-gas shift reaction to extract even more pure hydrogen.
Once we actually have it, we realize its physical and chemical properties are just astonishingly unique. First off, it is exceptionally lightweight. To put it in perspective, 1 liter of hydrogen weighs practically nothing, just 0.0899 grams. And if you ignite it, it burns with this beautiful pale blue flame. But here's the really fascinating contradiction. At room temperature, it actually isn't very reactive at all. The bond holding those 2 hydrogen atoms together is incredibly tough, acting almost like a microscopic steel volt. It has a massive bond dissociation energy of 435.88 kilojoules per mole. You literally have to pump a ton of energy into it just to break it apart so it can react.
But it turns out certain metals have a secret trick for dealing with hydrogen, bringing us to a really fascinating concept called occlusion. Certain D-block metals, specifically platinum, palladium, and nickel, can act almost like a metallic sponge. They can absorb massive, and I mean massive volumes of hydrogen gas directly into their solid lattice structure, forming what are called interstitial hydrides. The metal literally traps the hydrogen gas right inside itself. It's wild.
And we actually put those reactions to work in our everyday lives. Hydrogen is a phenomenal reducing agent. For example, in the food industry, it's used in the hydrogenation of vegetable oils. This process reduces the double bonds in polyunsaturated oils, which practically prevents your cooking fats from oxidizing and going rancid. And looking toward the future, we're pumping it inside advanced fuel cells to directly generate clean electrical energy, a real game changer.
But when we want raw power, we just let it loose. 4,000 Kelvin. That is roughly 6,700 degrees Fahrenheit. When you use an electric arc to dissociate those tough hydrogen molecules into atomic hydrogen and then let those atoms immediately recombine on a surface, they release a staggering amount of heat. These atomic hydrogen torches are used for heavy-duty industrial welding and cutting, melting right through thick metal like it's butter.
Section 3. The hydride connections.
You know, hydrogen doesn't just exist alone or in metals. Under the right conditions, it actively combines with almost every other element on the periodic table, well, except the noble gases, to form compounds we call hydrides. If we look at the p-block elements, hydrogen has 3 distinct friend groups. First up, the electron-deficient hydrides, like those formed with group 13 elements. They simply don't have enough electrons for normal bonds, so they act as Lewis acids, always eager to accept electron pairs. Then, we have the electron-precise hydrides, like group 14 elements, such as carbon forming methane, with a perfect tetrahedral geometry. And finally, the electron-rich hydrides, with groups 15 to 17, where there are excess, unshared pairs of electrons.
It also forms entirely different relationships with the other blocks. With the highly electropositive s-block elements, like sodium or calcium, it forms strong salt-like ionic bonds. And with many d-block and f-block elements, it forms those metallic or non-stoichiometric hydrides we mentioned earlier. What's completely wild about these metallic hydrides is that they actually conduct heat and electricity, albeit, not quite as efficiently as the pure metals themselves.
Section 4. Water, the river of life. But out of all the compounds hydrogen forms, its ultimate masterpiece is absolutely water. Without hydrogen, there is no water, and without water, there is no us. Crucially, water makes up about 65% of the human body, and an astonishing 95% of some plants. To understand why it's so special, we have to look at its geometry. In its gas phase, a water molecule has a highly polar, bent structure with a very specific bond angle of 104.5 degrees. But when it freezes into ice, it completely transforms. It creates a highly ordered 3D hydrogen-bonded structure. Each single oxygen atom becomes surrounded tetrahedrally by 4 other oxygen atoms at a precise distance of 276 picometers. This creates an open, spacious lattice, which is exactly why ice expands and uniquely floats on liquid water.
Water also possesses what I like to call a chemical superpower. We call this its amphoteric nature. This basically means water is an absolute chemical chameleon. It has the rare ability to act as an acid when it's mixed with a base, like ammonia, but then it turns around and acts as a base when it's mixed with an acid, like hydrogen sulfide. It just adapts perfectly to its chemical environment.
Furthermore, water is basically the ultimate solvent, because it has a very high dielectric constant, which means it's incredibly good at insulating electrical charges from one another. It has this intensely strong hydrating tendency. It easily rips apart and dissolves a lot of ionic compounds through a process called hydrolysis. And from those aqueous solutions, many salts can be beautifully crystallized into various hydrated salts, trapping water right inside their solid crystal structures.
Okay, we've covered a lot of dense chemistry today, I know, but I want to anchor all of this back to an emotional level. The source material refers to water as the river of life. And honestly, that really says it all. The intricate bonding, the strange angles, the amphoteric chameleon-like properties, all of this complex chemistry perfectly orchestrates the very foundation of our living existence.
So, as we wrap up this explainer, I want to leave you with a thought. Do you look at a simple glass of water, or the stars in the night sky, a little differently now? From the fuel that fires the cosmos to the bent molecules hydrating your body, hydrogen truly is the rebel element that makes the whole universe work. Thanks so much for learning with me today, and keep asking questions.